Good morning, Year 10. How's it going, guys? We're up and running. Cool. I'm in school, as you can tell. Sorry about the echo. I'll do my best to try and lower my voice a little bit, because I think if I lower my voice, it means that it'll probably come across a little bit clearer. I'll try and slow down as well. Lower. Cool. My video's up and running and is working well. I can close that. I've popped out the chat, so that's there. Hello, Mr. Duncan. There's Jassim. Oh, nice to see you, Jassim. Oh, Jassim's one of my ex-students. And he went off to university last year. It's good to see you, Jassim. How's it going, dude? Right. So today, guys, we're doing electrolysis. So I'll share my screen. Let's crack on. Let's crack on. Right. I'm from Nottingham. Ah. Wow, all the way from Nottingham. Are you there? You're not there right now, are you? 9:30 a.m. That's going to be like midnight your time. More like 1 o'clock in the morning your time. Wowza. Crazy. Right. I think I've shared my screen. I think that's all up and running. Yep, there we go. So 4 learning objectives today. Oh, wow. It's late. Right, okay, guys. So, electrolysis, GCSE, lesson 1. So, actually, can I just point out, the lesson actually has another title, which is molten. Yeah, we're looking today at molten electrolysis. I'll explain the molten bit when we get there. But 4 learning objectives today. So, number 1, know the definition of electrolysis and be able to understand it really from a decomposition perspective. The next one is to understand electrolysis in regards to oxidation and reduction. That's important. The next one is be able to predict products of molten electrolysis. I'd like as well to assign them. I'll change the thickness of my pen. I'll reduce that. Also, I want to do them to their correct electrodes. Yeah, link to panic. There you go. And you'll understand panic shortly. It's an electrode trick to help remember it. Some teachers teach pancake. I don't really like pancake. I prefer panic, because students always panic with electrolysis. They think it's really, really tough. And it is. It can be challenging. It's a challenging topic. And the last learning objective is to understand aluminium extraction. I'm also going to cover 2 other molten electrolysis processes, looking at it from a sodium chloride perspective and a lead bromide perspective. And I'll explain both of those to you and why we're choosing them. Are you back in school? Yes, I am, Winkit. Winkit's one of my year 13s, folks, if you're wondering. This is amazing. I've got everyone joining in on the lesson today. It's brilliant. Okay, so first thing I want to do is I want to define electrolysis. Now, notice that this has just come. This topic has come from the end of the ionic topic. Yeah, as you teach chemistry, there are certain topics which come in. It's good to put one after each other. We've just finished ionic bonding, and this comes immediately after in my eyes. I feel like this is the right place to do it. So the definition, and put this in your notes, the definition of electrolysis. Now, what I'm actually going to do is I want to it's nice for me to, I've split the word into 2. Now, what I'm going to do is I'm going to write the definition next door, and I'm going to do this in green. Yeah, electrolysis. The splitting of ionic compounds, using electricity. Notice electricity. Notice how it's specifically for ionic, which we've just finished. And so hence why this is important to do this immediately after. The splitting of ionic compounds using electricity. So the reason why now electrolysis is one single word. There isn't really a gap here. But I just wanted to explain to you that the word lysis, just going to change the thickness of my pen. The word lysis means to break. Yeah? It actually, and in this case, we then switch it for splitting. You can change that. The word lysis means to split. I quite like that. And the electro is telling you what's doing it. Now, electricity. Electricity. There are other lyses out there. I'm just going to give you a couple of extras. Now, these are really nota benes, so we can add these. I'm just going to put note that it's ionic, nothing else. Yeah, just want to show you a couple of others. So others include. So this is a nota bene. Nota bene. I love my nota benes. Nota bene. Say with an Italian accent, even though it's not actually Italian, it's actually Latin. But it sounds like you should say it. If anybody ever asks you what I mean, nota bene. Yeah, you get it. So other ones include hydrolysis. Hydrolysis. So this one means to split a compound. Notice how it's no longer ionic. To split a compound using water. Isn't that cool? So we pick up the lysis, meaning to split, yeah, and hydro, I could color code it if I can. Yeah, I can color code this. And the hydro, meaning water. I always think it's quite nice to see these other examples of lysis out there. I just thought I'd throw that one out there just for fun, really. It's nice to be able to see that. You're going to come across this, though, later on in chemistry anyway. So it's something. I'll give you another one more just for fun. Yeah, thermolysis. 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 And this is to split a compound, using heat. Using heat. Now, by the way, annoyingly, we don't tend to use that term, thermolysis. We tend to use a different term, which I'm actually going to be really emphasizing this. So in chemistry, we don't call it that. What we call this is thermal decomposition. So you never actually really see the thermolysis, but it's nice to mention it. And there's another one. We can do photolysis. Photolysis. And I wonder if anyone can give me on the chat what that one means. To split a compound using, I wonder if anyone can guess. Is anyone on the chat going to be able to tell me what it is? I'm just going to get my mouse out from my bag, by the way, folks. Give you a second to be able to answer that. I think if I've got my mouse. Yay! I've got my mouse. Using light. And Saru's on it. Well done. To split a compound using light. Isn't that cool? Loads of lysis. Yeah. So what we're doing today is we're doing I love that. Look at that. Navina, Zaina, Callista, well done. Spot on. Really impressed. Great job. Yeah. So lots of lysis, but today we're focusing on one particular one, and that's electrolysis. So we're going to split an ionic compound using electricity. Okay, so the next thing, molten. So molten. Okay, so the first thing is I do want to mention molten again. So molten simply means when a substance, it can be ionic, it could be covalent. In this case, we're looking at ionic. But when a substance is heated, until it becomes a liquid. So this is hot liquids, folks. Yeah, liquid. So just to show you an example of this, yeah, it's always nice to use the internet for useful things. So we can go molten, Google images, and it'd be interesting to see what it gives me. Excellent, it's given me a basketball. Fantastic. Let's do molten metal. Look at that. So that molten metal is a liquid hot metal to the point where it becomes, so it's so hot, you're talking here thousands of degrees at times. Yeah, melting point of, Melting point of steel, about 1650 degrees. That's melting point of iron. The melting point of gold, 1100. Melting point of silver, give or take, about 1060, something like that. Maybe 960. Yeah, not too close my melting points. But in order to get something to be molten, you've got to get it crazy hot. Yeah, this is very special, guys. Let's look at, by the way, other molten things. Molten glass. And you can see a commonality here. Whenever something is molten, it's often glowing orange. That's how hot these things are. Like, they are insanely hot. Yeah, so molten means a hot liquid. Let's look at molten aluminium oxide. Check this one out. I knew it was going to do that. It's gone into all like the understanding diagrams, which is not what I want. I want the picture of the sun, outstanding. Oh, they're not going to give me there. Look at that. Wowza. Aluminium casting. Nope, that's not the same thing. That's molten aluminium. Okay. But the word molten has very specific connotations. Yeah, a hot liquid. I'll put over here brackets, hot liquid. And by the way, very hot. Yeah. I'm tempted to give you like a temperature of like, you're talking in the thousands at times. Okay, so why is this so special? So key important facts from our ionic topic. So ionic compounds do not capitalize, notice my change and underline. Ionic compounds do not conduct electricity when solid. And we know the reason for this. Yeah, ions are not free to move. Notice my changing color. Ions are not free to move. But when it's molten, when molten, ions become free to move. Okay, so at this point, we now need to get into the real nitty-gritty of what's happening here. So what we need to do is we're going to take a ceramic basin. And what we're going to do is we're going to add to this. And what we're going to do is let's stick with something you guys know something about. Let's do sodium chloride. Everyone loves sodium chloride. Let's have a look at what it looks like. It is a white solid. Yeah, sodium chloride. So it's a white solid. There we go. Exactly what I want. Yeah, everyone recognizes it, everyone knows it. Now, what it's made up of, we know that sodium chloride is made from, it is a giant ionic lattice of Na+, Cl-, Na+, Cl-, Na+, Cl-. And this goes on indefinitely. And as a solid, these are unable to move. They're simply vibrating in a fixed position like this. So what we're now going to do, and I'm going to move that image now. Yeah, I'm going to put that over there. Yeah, I love the fact that I just left behind one of the little things. There we go. So this is what we're seeing right now. What we now need to do is we need to heat it. So we're going to add a boatload of heat. And we're going to heat this to 801 degrees Celsius. Can I just tell you how insane that temperature is? It be crazy. I don't know if you guys have ever had any experience of someone who's been injured by boiling water. Boiling water is at 100, and it damages instantaneously. It melts skin, yeah, and it's permanent. Well, imagine 800 degrees Celsius. It's actually very difficult. I can achieve that in a lab. It can be done, but it's crazy hard to do so. So once we heat this it will become a glowing red molten liquid. Yeah, this is going to become, yes, I was burnt once. Oh, Gayatri, I'm so sorry. My fiance also has a big scar from when she was a kid and she was burnt permanently with hot water. She spilt a cup, her mum was boiling a kettle and she was very young and she pulled it off the stove and it fell onto her and it burnt her permanently. It's very, 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 it's a horrible thing to have happen. So once we've heated this to 801, the state symbol changes. Yeah, we can now change this to the state symbol liquid. Now what this means is, no, it's fine. When it was healing, the skin broke inwards and it was weird. Oh, I'm so sorry. So once it's a liquid, the ions become free to move around. The ions become free to move around. And now what we're going to do is we're going to add some electrodes. So we're going to add some electrodes. Now, let's talk about the electrodes for a minute. So these here, I'm going to try and do my very best to color coordinate all this stuff. Yeah, I should be trying, I like coloring stuff in. It's always a good idea. And I'm actually choosing this color for a very good reason. Right, so guys, an electrode is an object that conducts electricity through an electrolyte. I know I'm adding all these new words to you guys now. We'll write all these down. I'm going to add this one in here as well. I'm going to color this one in. So these are our electrodes. So if we want to conduct electricity through something, we're going to need some properties of our electrodes. Yeah? What material on the chat, please? What material? So let's by the way, I'm hoping you're drawing the same image that I am. Yeah? So these here, actually, is that the best way of doing it? Yeah, these here are called electrodes. Electrodes. So the question is, if we want electrodes to be put into 801 degree molten salt, what would we want to make them out of? Key properties of electrodes. Number one, it needs to have a high melting point. I think that's very reasonable. Next, number two, they must be able to conduct electricity. Conduct electricity. Okay, and there's one more property, a good conductor that have a high melting point. Well done, Zina. There's actually one more, Zina. There's one more that's really, really important. They need to be inert. They need to be inert. So first thing I want to do is quickly remind us of what the word inert means. Yeah, the word inert means unreactive. Because the problem is, if you tend to stick something into chemicals at these kind of temperatures, they tend to react. They tend to do something. And we definitely don't want that to happen. So could anyone suggest a material that you guys all have in your school bag? Amazingly, you have this material in your school bag that would work well as electrodes. So the question is, could we use a metal? They're my high melting point. So this suggests a metal. Can we use a metal? The answer is no. Can I just point out at these temperatures, I mean, a good few metals will have melted by now, but also they're going to react. And this is the problem with metals. Metals at these temperatures will either melt or react, and we don't want that. So we can't use a metal. No, too reactive. You could choose a very unreactive metal. Could anyone suggest, knowing that we've just done the reactivity series as well before doing ionic, What metal might suffice here? You can put it on the chat. There is a metal. There is one metal that we tend to use, but it's very unusual to use it. It's only tend to be used. Lead. No, it's melted by this point, Callista. Good idea, but no. Lead will melt. Low melting point. We need something way less reactive than that, Callista. Go lower. Go way, way down the reactivity series. Well done, Zyner. So every now and again, no, too reactive, but I'll do it in green. But every now and again, yeah, but sometimes platinum. Now, can I just point out, you wouldn't use platinum in this case. Do we use redox electrodes? That's not a thing. Navina, that you've put two words together there, which don't really, like, it will be, like, redox itself means reduction and oxidation, and they will be happening at the electrodes, but that's not, you can't, like, call it a redox electrode. It's not something you'd do. By the way, platinum, though, way too expensive. Way too expensive. Most people don't use it. There's a better choice. Now, you guys definitely don't carry platinum in your bags. So what do we use? There's one material which you guys all have on you in school every day that is suitable. And that is graphite. Graphite. Check this out. Graphite electrodes. Graphite electrodes. There they look how massive they are. It's insane. Look at that. It's hilarious. They're absolutely huge. Shows you how much of these we use. Isn't that absolutely bonkers? Graphite electrodes. Look at that. They have an insane, you use carbon electrodes. Well done, Callista. Well done. Yes, use graphite, carbon. Yeah, and these, because graphite has a melting point of 4,000 degrees Celsius. Let's make some notes. Graphite electrodes. Fact number 1, melting point. Melting point 4,000 degrees Celsius. You can put that, there's only one other material that beats graphite, and that's diamond. So, you know, you're going to be able to do this under any circumstances. It can always be used. Number 2, conducts electricity very well. Conducts electricity very well. Very well. Number 3, it is inert. It doesn't tend to react with anything. Yeah, inert. And number 4, it's cheap. No. Do you know that China own pretty much all the graphite electrode mines? I know, they kind of own all of them. You need to mine certain types of graphite, really good high quality graphite, and all those mines happen to be in China. But so we're going to use graphite. Now, what we now need to do is realize that there's actually 2 different electrodes. So we can do electrodes. So we have number 1, the cathode. The cathode. Now the cathode, I'm going to color coordinate this. Let's do cathode. Hence the ode, by the way. Yeah, electrode, cathode. So the cathode is negative. The cathode is negative. Why is it called the cathode then? Because it attracts. Cathode attracts cations. Yeah, it attracts the positive cations. Yeah, and then we've got the anode. Nope, anode. And the anode is positive. Why is it called positive? Why is it called the anode? It attracts anions. Yeah, it attracts anions. Don't like that it wasn't red. There we go. It attracts. So you realize where the names come from. So people often go, I'm never going to remember this. And this is where panic comes in. So positive anode, negative cathode. I really like panic as a method of remembering it. It just always worked for me. Positive anode, negative cathode. Panic. I can do that. And that I genuinely can't stress how useful it is. Super handy. Learn. I'm going to put that into a yellow spangly box and say, learn this. Yeah, so useful. Cannot stress how useful this is, because what they're going to say is, they're going to say, write the redox equation that's happening at the cathode. And you'll go, oh, what's the cathode? Positive anode, negative cathode. The cathode is negative. It's going to attract the positive ions. Okay. And it makes everything so much easier. Okay. So next, redox. So now what we need to do is, I don't want to rush you guys. How are we doing for time? We're doing okay. Doing okay. How are we doing for time? Just going to quickly check the time. Halfway through? I think that's okay, isn't it? Yeah, look at that. Okay. So now that we've got that, what we now need to do is look at this from a redox perspective. Zoom in. Zoom, zoom. Right. Okay. Let's add some electrodes. Add some graphite electrodes. Okay, I'd love to be able to. I feel like that's not good enough, but not that it really matters. Right, there are our electrodes. I really want to try and make them nicer to say. I wish I could do that better. I'm sorry, guys. I don't know if I can fill shape or not. Maybe I could try something new for me. Fill? Can I fill it? Can I fill it? Who knows? Shape? I don't know. Ink to shape? I don't know. It suggests that I could. I don't know. I don't know. That's rubbish. Fill? Go on, fill it. What's this? I don't know what that is. I don't know what's going on here. I haven't got a clue. Oh dear. Whatever. Right. Sorry guys, I'm ruining this, aren't I? Okay, so a couple of electrodes. Oh. Do you know what? I quite like the fact that I make them different sizes. It just means that we can tell them apart more easily. I think there's some value in that. Right, let's add our molten solution. Let's add our molten solution. Okay. So what we now have here is, now let's look at this from a sodium chloride perspective. So in here, by the way, let's hook up our electrodes. I don't know whether or not you guys know this, but the bigger line on the battery symbol is going to be positive. I don't like adding in the circle now. And the smaller one is negative. Yeah. So now we can run panic. Yeah, panic. Positive anode. So this one's the anode. Negative cathode. So this one here is the cathode. Do you see what I've done? I've looked at who's connected to what. This electrode here, this electrode, the purple electrode, yeah, this purple electrode is connected to the negative terminal. So this is the negative electrode, and the negative electrode is the cathode. And then on this side, the positive terminal of the battery, are they actually different sizes? No, they're not, designer. They're not actually different sizes at all. They can be different objects, but we'll come to that later on. Yeah, it's just nice to be able to see a difference. That's all I'm trying to do here. Okay, so we've got an anode and cathode. Right, let's put in my ions. Let's put in our anions, a negative ion, Cl minus. Let's show its electrons. Let's show just its outermost, only care about its outermost. There we go. And let's show sodium. Sodium lost its outermost electrons. Its outer energy level is empty. Yeah, it's actually quite a nice way of looking at it, isn't it? Okay, and I'll put the plus inside it. Okay, there we go. So now that we've got our ions, we can now see where each of them is going to go. So first bullet point, ions are attracted to the electrode, with the opposite, with the opposite charge. And this is due, brackets, electrostatic attraction. Electrostatic attraction. Opposite charges attract. We know this. So, the anion, the chloride anion, is going to wander over to the anode. Yeah? Because that's where it's going to be attracted. The sodium on the other hand, I'll make that thicker. The sodium, on the other hand, is going to make its way over to the cathode because it's a cation. So what now happens at each place? Right, let's zoom in. Zoom. Right, let's see what's happening. So here's our electrode. Here's our graphite. I'm going to change that a little bit. I'm going to put it up to here. That way I don't have to color in quite so much. Lol. So here's our graphite electrode. Okay, and the electrode itself is, sorry. I really wish it was easier for me to color in these things. If I just go that one and make it massive. It's a slightly different gray, but who cares? That's a bit quicker, isn't it? Okay. So there's our electrode. And here, now, so this is the anode, and the positive anode. Okay, panic. So this is the positive. Let's switch back to small and black. This is the positive anode. Panic. Yeah. And what we've now got is the anion. We've got chlorine. And in fact, let's draw two of them. So the chloride ion, now be careful, it's not chlorine, it's chloride. Yeah? And here's another one. The chloride ions are going to be attracted towards the electrode. And when they strike the electrode, when they hit it, when the chloride ion strikes the electrode, what happens is that little cross of an electron, the electron that didn't belong to it, is physically ripped off. It's ripped off that I'm going to do it as a cross, like that. That electron here, that electron there, the extra electron is literally ripped off it. So when it gets ripped off it, you suddenly realize that the chloride ion actually becomes a chlorine atom. So if you actually look at what happens with the two of them, by the way, do you notice it's getting smaller to boot? When this one hits the electrode, I'm trying really hard to have it, there we go. So when this one hits it, it also loses its electron. It is physically ripped off it by the electricity. The electricity physically rips it off. Now, what you realize is that these two, we've now got this situation. The chloride ion is becoming, a chloride ion is becoming a chlorine atom and losing its electron. So this is here is a chloride ion, And this is a chlorine atom. Now, here's the thing. Chlorine atoms. So, by the way, is this... Oh, I'll put this out to the chat. Who's going to remember? Oxidation or reduction? Oil rig. Everything goes back to oil rig. Oxidation is loss of electrons. Reduction is the gain of electrons. And the word gain has in it. Well, I'm pretty sure that's not going in, but in fact, it's coming out. Yeah, so well done. Thank you, Zina. Well done, Julius. Well done, Massaro. Oxidating. I love a good bit of oxidating. That's excellent. Well done, Lauren. Well done, Callista. It's amazing. Well done. So this equation here is oxidation. This here is oxidation. Now, here's the clever bit. That reaction there that you can see is not actually going to happen. What's going to immediately happen is it's going to happen twice. And they are going to pair up. So here's what actually happens. Two chloride ions have their electrons ripped off them to form chlorine atoms. Oh, I'm tempted to show this like this. Two chloride ions have, oh, I'm going to do this even better. Hang on a sec. Yes. Two chloride ions have their electrons physically ripped away by electricity. These are torn away from them and they immediately pair up. I should have done it as the other way round. I know, I'm sorry. I'm going to adjust it. That's me not doing a good enough planning job, is it? Let's reorganize that one. You realize it doesn't really matter. There we go. I'm going to go. This one is all crosses. Yeah, all crosses and a dot because I'm just showing that so this one is going to lose this electron. Yeah. I'm just going to put the Cl in there. And we're going to lose 2 electrons. Yeah, that's what's happening here. And this guy's going to lose this electron. Yeah. So the equation becomes 2 Cl minuses going to a Cl2 molecule and 2 electrons. They immediately pair up because they want 8 electrons desperately. So they're going to link together to make sure, because in sharing, in this scenario, both chlorine atom, this chlorine atom here has 1, 2, 3, 4, 5, 6, 7, 8 electrons. It's happy. Yeah. And this one, this chlorine here has 1, 2, 3, 4, 5, 6, 7, 8. This one also has 8. It's also happy. So they will immediately link up. And that's the equation I need you to learn. Yeah. Now I'm hopefully going to teach you so you don't have to learn them so you can build them. But that's a useful thing to happen. And this is oxidation at the anode. So the positive anode, the problem is this, isn't this covalent? Yes, Zina, it is. It becomes covalent. Yes. Yes, it does. And I know we haven't done covalent bonding yet. I know. It is. We'll come to that later. But I'm doing this properly, showing you all the electrons and how this is happening. Technically, I don't need to show you the covalent bit, but I think it's important to do so. So we've just seen what's happening at the positive anode. What we now need to do is look at what's happening from the negative cathode perspective. So let's zoom in. Zoom, zoom. Let's zoom in. Don't know, it's too big. Let's zoom in. Let's zoom in. We're nearly at the end of the lesson. Let's zoom in. Right, so what does this one look like? Oh, it's going to ruin that, isn't it? I'll do. Right. So now we're going to swing over onto the other side. We've got another graphite electrode. Got another graphite electrode. But this time it's the opposite charge. Yeah, this time it's the negative. Yeah. So how do I remember this? Panic. I always return to, just like I always return to oil rig. Panic. Positive anode, negative. This is the negative. I'm going to rotate my little tablet. Negative cathode. Okay. So what's now going to happen to this? Now, because this is a negative electrode, yeah, it's going to attract the positive sodiums, who now have an empty outer shell. Now, this is going to wander over, and it's going to hit the electrode. Now, what's going to happen now is it's going to strike the electrode, and it is going to gain back its electron. And it's going to become a sodium metal atom. The Na plus will gain one electron to become sodium metal. So it started off at sodium, where it would actually, yeah, it's just going to become, I don't need the state symbol really. So is this oxidation or reduction? I always go back to oil rig. Every time. It is such a panic. Oil rig, so useful. Stick with them. Oxidation is loss. I'm not losing here. This is gain. This is going in. It's on the left-hand side. It's a reactant. Reactants go in. Yeah. Reactants go in. Products come out. Yeah. Products come out. So this is reduction is the gain, and it has the word in it. Yeah. So this one here is reduction. This one is reduction because it's gaining electrons. So what now happens as a result of this process? What are my two products? So this is where I'm going, okay, so we can tick off my learning objectives. Got the definition, understand it from an oxygen. We now understand what's happening, predict the products. This is where things become a whole lot easier. That's the hard bit. If you can get that, you're halfway, you're more than halfway there. Right. Products. Products of molten, notice my capitalization, molten electrolysis. Electrolysis. Right. We've taken sodium chloride and we have liquefied it. We have made it molten, hot liquid. Right. We're now going to decompose it. We're going to rip it in half. Is in one of the previous lessons, you told us that the electrons lost from the negative ion travels through the anode to the cathode and gains on. Yes, that is correct, Zaina. So in reality, the electrolysis process, the power pack, the battery of electrolysis is acting as a pump. Is the same electron gained on the positive ion the one that's lost on the negative? Yes, it is. Yes, Zaina, it is. That's exactly right. I need to slow it down. So when this negative ion over here, when that hits it, look, it's now waiting to lose its electron. There's the positive ion, and watch, there's the electron, comes down and hops back over. Yes, the power pack is simply full screen snip. And look at the chlorine disappearing off. This here is simply acting as an electron pump. That's all it's doing. Yeah, we rip the electrons off the negatives, rip those electrons off. The pump pumps them around the circuit and drops them back off when a positive ion gets there. Yes. Oh, okay, makes sense. Cool. It's just an electron pump. That's it. That's what a power pack or a battery is. So it's still going. Lol. Stop. Lol. So we can now predict our products. All we're going to do with molten is, this is easy. Predicting products of molten is easy because all you do is rip them in half. So we're going to start with sodium chloride. And what I'm going to get is sodium metal, and chlorine gas. Chlorine gas. It literally, chlorine gas, it literally, electrolysis rips them in molten electrolysis, it rips them back into their elements. Yeah? And then we can balance the equation, 1 Na, 1 Na, 1 chloride, 2 chlorines, 2 atoms there, double it and double it, there we go. So let's predict the next one. Let's now take now this, I'm thinking you're going to suddenly realize how easy this is. I'm going to take aluminium oxide. Aluminium oxide. It looks like aluminum. Aluminium oxide. I'm going to run electrolysis. Electrolysis. I'm going to split it, and that's liquid. What am I going to get? Blank plus blank. Please complete on the chat, please. Next, we're going to separate lead bromide. PbBr2. This is lead bromide. What am I going to see when I run electrolysis? I've lost my mind. It's lockdown. Sorry, folks. Yeah, what am I going to get? Come on, folks. Don't overthink it. Owen. What a ledge. I love your little arrow. That's boss. Well done. Absolutely correct. I'm going to get aluminium and oxygen gas. Owen, can I say how impressed I am of you remembering the two? Well done. I'm going to rip the aluminium oxide into two, and I'm going to make aluminium and oxygen gas. And by the way, the aluminium will come out as a liquid and the oxygen will come out as a gas. Let's now balance the equation for electrolysis. So common denominator 2 and 3, it's awkward actually, because what we need to do is we need to balance that one first. I'll make my pen thicker. Yeah, so 3, 2, and 4. There we go. Well done, Julius. Well done, Ziner. So guys, on to the next one, lead bromide. I'm going to rip it apart. It's molten. Yeah, I'm going to take lead bromide. I'm going to take it, I'm going to heat it to become a liquid, and then I'm going to pump electricity through it. And what am I going to create? Let's do a whole load more just for fun. Let's take potassium iodide. Let's make that a liquid. I'm going to then become electrolysis over the top. Let's rip it apart. What am I going to get? Right, next. Let's do something else. Let's do something like, I don't know. Let's do calcium sulfide. Why not? A bit of CAS. I'm going to take calcium sulfide. I'm going to rip it apart using electrolysis. What am I going to get? Yeah, you get the point, don't you? How easy is this? You just go, what elements is it made from? Lead, Pb, and Br2. Well done. Balance it. Oh, it's already balanced. I'm going to make liquid lead metal, and bromine's going to turn into a gas, even though it's a liquid at room temperature. This is being done at over 600 degrees Celsius. The bromine's going to become a gas, and the lead becomes a liquid. Potassium iodide. I'm going to form liquid potassium metal. That's a really, really bad idea, by the way. That's like explosive when it's a solid, let alone when it's at 500 degrees. It's a really bad idea. Iodine. Got to balance it now. Yeah, so that becomes a 2 there and a 2 there. Oh, calcium sulfide. I'm going to get calcium metal. I'm going to get calcium metal, but as a liquid. And I'm going to get sulfur as a gas. Sulfur's going to come out as a gas. Just to tell you, by the way, sulfur's really awkward. It travels around in 8s, but you do not need to know that for GCSE. So don't worry. Cool. So we can now predict the iodine's going to be a gas for sure. At these temperatures, most of the non-metals come out as gases. We can now predict the products of molten electrolysis. I'm going to pick up aluminium extraction next time. I think that's worthwhile doing. We'll spend a bit of time on aluminium extraction. So I'm going to leave my lesson there today. I just thought I'd show you this cool picture. This is this is actually the aluminium oxide electrolysis plant. And I just want to show you that in this diagram. So here, that there is molten aluminium oxide, molten Al2O3. Look at it glowing red hot. And then this massive square object here, that there is the graphite electrode. Massive graphite electrode. It's kind of cool to see it. And the guy's stirring it. kind of neat, really. This is done at 1,000 degrees Celsius. Crazy high temperatures. But it's just really cool to see this and how big everything is. And this, look at the factory. The factory just goes on forever. They're massive. This is because we love aluminium. Everyone loves aluminium. Light metal, lightweight, corrosion resistant. We love aluminium. It's great now. Right, guys, I'm going to leave you be at this point. I'm going to end my lesson here. It has been a lot of fun. I hope you found it useful. I will set you some questions for homework. And it's basically just, it gives you the compound, and will tell you molten, and then it will say anode, cathode, and you've got to identify which one goes where, and then write the half equation for it. It's tricky. We'll do some more of that next lesson, but we'll go through that homework as well. Anyway, guys, have a nice rest of your day. I'll see you all soon. See you later, Winkit. Oh, see you later.